Welcome to Dynamical Systems, Lecture 4. During the previous lecture, we looked at bifurcations where we had one parameter parameterizing the differential equation on the right-hand side. What we'll do today is look at bifurcations that occur when you have two parameters. Specifically, we'll be looking at one example that describes insect outbreaks and effectively any mechanism that switches on in a semi-permanent way. Okay, for those that are following in Strogatz, this is chapter 3.7 in Strogatz. Okay, so insect outbreaks typically occur when you have a population of insects that have a normal sort of level, and then something happens and suddenly you have this massive plague happening that can do a lot of harm to the vegetation. An African example is the locust on the eastern coast of Africa that just breaks out and then basically decimates the environment. And for obvious reasons, you want to avoid this, and this is why these things are studied. So the example that Strogatz uses in chapter 3.7 was originally worked out by Ludwig et al. In 1978, and it was published in this journal on volume 47 on page 315. So this is just an example of a standard reference. For example, if you're doing a problem set, you would want to write it like that if you were to actually use a type of or any reference. Okay, so it's an example of a bifurcation problem using two parameters, as I've just mentioned, and in these cases you can have phenomena that did not occur when only one dimension parameter is possible. And it has sudden outbreaks. In other words, it can capture enough details to actually have these cases where you have suddenly flare up into a very high population that then is basically disastrous for the environment. Mathematically, this means there are jumps in the nature of the solution. And as we go through the example very carefully, we'll illustrate how these arise, because that's an important part of the problem. Okay, so the original problem was that this paper up here that Ludwig wrote about was a problem of budworms or spruce budworms that happened on the forests of East Canada. So what happened was, or rather this even though this is the original problem, it has the actual model that they developed has wide application and can be applied to many other problems in understanding insects outbreaks. An example, as I've already mentioned, is the locusts on East Africa's coast. It can also be applied as a model that will describe internet fame. For example, Master KG with Jerusalem was basically an outbreak, and once the dude's famous, it's very hard to become unfamous, but it actually obeys the same mathematics. Okay, so what you need in the model, or a problem that eventually arises in this model, is two different timescales. So what happened with the spruce budworms in Canada was that the forests always have spruce budworms, so it's not as if it's a new insect that occurs. Then something suddenly triggers them, and they go from a population that's normal and just eating a few leaves to a population that actually eats up the whole canopy. And so the problem was, is there a way to stop this? In other words, can we, for example, breed the birds that eat the budworms so that we don't lose all our forests? And that's what caused old Ludwig et al. To start looking at this research. And this is how he analyzed the problem. The first thing he said is there are two different timescales. So the one is that insects multiply very rapidly on a time scale of weeks, which they call the fast time scale, and they can reach very, very large populations within months. The vegetation, on the other hand, which is like the forests or the grass or crops, if you're looking at the locust, they grow very slowly, and we call this the slow time scale, and it's of the order of years. For example, for a tree to grow, it's 1,000 years. For a tree to replace all the leaves in its canopy, it takes 7 to 10 years. And for a crop, it takes 1 year. Okay, and it's these interaction of these time scales that actually have an important impact on the type of the way the outbreak occurs. So the model Ludwig et al. Proposed to describe the outbreak of budworms in the forest was as follows. Okay, he said let n of t be the population of insects as a function of time. And then he made up the model. He said it's n dot of t is equals to Rn times 1 minus n over k minus some function p of n. And the reason why he chose it that way was, if you recognize this, I think from the second lecture, this is just your logistic growth model. So here we have sort of what the population would obey like if the only things you were considering was how rapidly they multiply, which is the growth rate, and what the carrying capacity was. In other words, what is the maximum population they can reach for a certain amount of food. And that is your logistic growth model. So what this person is now adding is a second term that indicates how quickly the predators, say for example the birds, are eating the budworms. Okay, so just to understand what's happening here is the logistic growth minus the death rate due to predation. And while actually building this type of model is not the focus of this course, we're focusing more on analyzing the equations, it's very, very useful to gain insight into what we're actually exploring if you know where the model came from. And a general rule of thumb when building these models is you try and fit in the simplest possible model that can capture what's going on. In other words, the simplest possible model for a population growing with a fixed carrying capacity or fixed resources is this thing in green. It's a logistic growth model. And then you know you've got to add something else, so you add this predation term. Okay, so now I haven't yet specified the predation term except to say that it's a function of the population. So I'm now going to talk about the considerations they use to specify the predation term. Okay, so the first thought was the predation term turns on sharply after a certain insect population, say n equals to a. So the thinking behind that is initially the birds don't know to look and eat off the budworms because they don't recognize them, there's so few of them. But after they become visible and the birds start knowing they taste good, then they suddenly start eating the budworms a lot, and so the number of budworms eaten by the birds increases. Okay, and the second consideration in this model was that the predators cannot eat more than at a maximum rate. So if there's a lot of budworms available, then each bird can only eat a certain amount before it's full. And so eventually for a fixed number, because the birds multiply much slower than the budworms, for a fixed number of budworms, a fixed number of birds, there's only a maximum number of budworms that the birds can eat. And that maximum we're going to call B. Okay, so this is the functional form that they basically chose to explore for this particular model. And the reasoning behind that is just what I've said. So let's just plot that. Firstly, if n goes to infinity, in other words, when the number of budworms or the insect population gets really large, you can see that below the line, it's this n squared that dominates and basically cancels the one above in the line. So the limit as n goes to infinity is simply B. Okay. So as n goes to infinity, the predation model approaches B, which is the maximum rate at which the predators can eat the prey. Now, if n is very, very small, remember as n goes to 0, we said predation only turns on after the population is about equals to A. So we only expect a reasonable size of the predation to occur over here. So as n goes to 0, we see that this thing behaves basically like b over a squared times n squared. Okay, and that's what we have. This is the limit as n approaches 0. The first order term is that the predation is basically quadratic in n. And so we would expect the graph over here to be a parabola, and then it would go up, have a point of inflection, and eventually asymptote to that level over there. Just one point we can put in the graph. When n is equals to a, we see that p of n is equals to b times a squared over 2a squared, so it's going to be equals to b over 2. So there's this point that it has to go through. So we roughly have a parabola that goes through b over 2 and then asymptotes to this line equals to b. So there we put in what the predation model is. And as I said, this was the simplest guess that they could find that was reasonable for a predation model. So we've now modified our model from just not logistic growth that ignored predators to a model that includes both logistic growth and the predators eating the birds. Okay, so there we go. We now have our full model. And this model has 4 parameters. It's basically R, the growth rate, K, the carrying capacity, and then the 2 parameters that go into the predation, namely the maximum rate at which the birds can eat the budworms and the point at which they actually start eating them. Okay, so there we have it. R is the growth rate, K is the carrying capacity. These are constants, and these 2 are basically assuming no predators. And A and B depend on the predators, in other words, the birds. Right. So what we have now is a reasonably complicated model that we want to analyze. Okay. And the question is, as we often do in dynamical systems, can we determine the long-term behavior of the number of budworms as a function of t? And more importantly, can we eventually understand it well enough that we know how, if we changed one of the parameters, how this behavior changes, because ultimately we want to control the population of budworms. Okay, so you want to understand it as a function of the various parameters. So it's not just a matter of choosing parameters and getting an answer. We actually want to know it for all the parameters. And when we have a problem like this, it's quite tricky because you have to explore all 4 of these parameters in the parameter space. And the first thing we do before we do that is we try and simplify it. Okay, so 4 parameter space is a really hard problem. The question is, what the first step we take is we try and simplify it. So we can try and simplify it by what we call non-dimensionalizing. So what that means is we reduce the number of parameters without reducing the complexity of the problem, because we sort of analyze these equations and we try to see if there's a way of combining parameters that we don't change the problem at all, but we actually get a simpler equation to analyze. Okay, so we're going to reduce the number of parameters to meaningful combinations and rescale the variables. So what we can do is, the first thing we should notice is there are 3 things that identify a population. So the first one is the number of budworms itself, which is a population, but that changes with time. The second thing we can identify is that K is a constant, also represents a population, is the carrying capacity. It's the maximum amount of budworms the forest can take, or at least sustain, without them being eaten. And A is the number of budworms, or the population of budworms that have to be there before the prey or the predators start being alert to the prey. So A is also a population. Okay, so a natural thing to do is to say, okay, let's define a new variable where we have the ratio of n, the population, over A. In other words, the time at which the budworms initially become visible. Okay, and we're going to call that a dimensionless population. And then we're going to say n of t is now equals to A times x of t, where x is a new dimensionless population. So we've just rescaled the population by a constant, and that constant was chosen to be A. Okay, What we then do is when we have to put this into this differential equation up at the top, we need the ndt, and we have to express that in terms of x, which is now going to be our new variable. So we have the ndt is simply equals to a times the x dt, because a is a constant. Okay, and so we can now use this to rewrite this equation up at the top simply by replacing n with the ndt, n with ax. We can have, and the derivative with this expression over here, we have that the ndt is simply a times the x dt, and that is equals to r n, which is now ax, times 1 minus ax over k, minus b a squared x squared, a squared plus a squared x. Okay, and this we can then simplify, and the reason why we chose x in the following way to be the new parameter is because it simplifies the most complicated term. So if we look over here, we see that the a's cancel over there, and we can further, if we divide by b, we can simplify it even further. Okay, so then we simplify the most complicated terms, so the a's cancel, we divide by b, and therefore this term has no parameters in it at all. And generally that's what I go about doing. I make sure that the things are dimensionless. In other words, I divide populations by a parameter that is indicative of population. I could have chosen either a or k, or you could try them both, but it just turns out a gives the better answer. And then I put the assumption in here, and I see what else I can do. And what else I can do is divide the whole equation through by a constant, which in this case is b, and then simplify the thing. So if I divide this by b, I simply have a over b, the x dt is equals to r a over b, x times 1 minus ax over k, minus something that now no longer has a parameter in it. Okay, so it's a very good guide to try and simplify your most complicated term. Okay, so that thing no longer has a parameter in it. The next thing I can do, and we call that dimensionless, the next thing I can do is rename the parameters, okay, because they now appear in combinations. So a over k is once again dimensionless because both a and k are populations, and I'm going to call that 1 over little k. I can also call this thing that appears in front over here, r a over b, is also now a constant, and I'm going to call that little r. Okay, and they are both dimensionless. Both these parameters are dimensionless, and what we can have next is to rescale the time, because I have a parameter entering in here as well, and I can even simplify it further, and I can rescale the time by saying let tau be the new time, and that's equals to alpha t. And if I do that, the derivative with respect to time then just becomes d tau times d tau dt, and d tau dt is just alpha. Okay, so this time derivative is then just d dt is then just equals to alpha times d tau, and so if I choose alpha to be b over a, then I can simplify this thing even further. Okay, so if I choose alpha to be b over a over b times d dt is then just equals to d tau. Okay, and then the equation that I'm left with is this dx d tau is equals to rx 1 minus x over k, using these two definitions, minus x squared times 1 plus x squared. Okay, and this is with respect to new time. So this thing only now has two parameters in it, namely r and k. Okay, and just to recap, k is simply the combination of the parameters a over k, and is called the scaled carrying capacity. And r is simply R times A over B, which is called the dimensionless growth rate. Okay, and now when we go about analyzing the equation, we do it just as the equations we've done before. We find the fixed points, namely where dx d tau is equals to 0, and we see that x star equals to 0 is a fixed point. And once again, as we've always done, is we have to write in the conditions where this fixed point exists for which parameters, and it's all of them. And the other fixed points must satisfy what remains. In other words, we divide by x, because we assume it's not 0 for the other fixed points, and then we find that the other fixed points must satisfy the equation r times 1 minus x over k is equals to x over 1 plus x squared. Okay, this equation is actually cubic for x, right? If you multiply through both sides by 1 minus x squared, you have a cubic equation. There is an analytic way to solve it, but you will have to use a computer to actually work out the roots. What we're going to do here is once again employ a graphical method, okay, simply because it's easier and you can very quickly get an answer. So the graphical method is once again you're setting two different equations equals to each other. This one on the right hand side depends on two parameters. This one on the left-hand side depends on two parameters, r and k. The one on the right-hand side does not. And the zeros occur when the two graphs intersect each other. So what we're going to do is simply plot this graph. So this thing is a straight line in x that looks like that. And we know that when x is equals to 0, y is equals to r. When y is equals to 0, we have that x is equals to k. So it's the straight line that joins r and k. Okay, and r and k are parameters that you put into your model, and you can change them. So wherever they're the two parameters, so you can change r, then the y-intercept moves up and down. You can change x, and k, and then the x-intercept moves left and right. Okay, so this is the line y1. The second thing is this thing on the right-hand side over here, which has the following form. If you want to plot this thing, remember what you're going to do. You know that is x goes to infinity, this thing goes to 0, it falls off like that. As x goes to 0, approaches 0, this thing basically starts behaving like a line that approaches the origin. Okay, and it has a maximum that you can work out by taking the derivative and finding where that thing is 0. Okay, so there we go. We now have a way of finding the zeros, and let's just explore it in greater detail. So here once again is our differential equation that we're solving. We have our fixed points, and we're going to say that f of x is equals to this function because it just makes it easier. Okay, the fixed point is either the 0 fixed point or the fixed point that obeys this property. And so let's have a look at what happens. Let us first begin if we have k that is small. So if k that is small, it's over here. We're going to plot the graph, and so there's small k. Let's plot this thing that doesn't depend on any parameters. So we pick k small enough that it's in close to the origin and under the big hump. And what we're going to do now is change r and see what happens. So if r is quite large, then this line is basically, by changing r, we move the y-intercept of the line. Okay, so we can sort of decrease r, and we see that this line, suppose we start with this line, it just moves. It moves flat, but it remains the fact that you only have one intersection. Okay. And we can increase r as well. And we can see that it remains. For that small k, you only have one intersection. For large k, it's a different matter. Okay. It's possible to have 1, 2, or 3 intersections, and let's see how that happens. So once again, we're going to plot y as a function of x. We're going to plot the graph y2 over x times 1 plus x squared. that doesn't change. And then we're going to pick k large over here, and we can see what happens as we decrease r. So as we decrease r, this line moves till it eventually touches, sorry, let's just go back. Oops. So firstly, if r is large, there's only one intersection. If we decrease r, eventually this line will become tangent to the hump, and we will have basically two intersections, this one and at the hump. If we decrease r further, and just one more statement, this intersection here is a bifurcation because the nature of the solution is changing from one fixed point to two, and this is basically the formation of a fixed point, of a pair of fixed points, a stable and an unstable one, out of basically nothing, and so it's a saddle node bifurcation, and we're going to call that S1. If we now decrease r further, we have three intersections, one here where the original one was for large r, and then the saddle node bifurcation that has basically split and become two fixed points. We increase it further, and we eventually have that the thing becomes tangent over here, and you have a single fixed point, which is also a saddle node bifurcation because you have two fixed points disappearing. Okay, so here you again have two fixed points, one over there and this one here. Okay, and we're going to call that S2, the second saddle node bifurcation. If we decrease r further, we see that we've lost the pair of fixed points and we're just left with one fixed point again. Okay, so this is the picture as we change r if k is large. So now we want to actually find what the values of S1 and S2 are and where the bifurcations occur analytically. And the way we do this is kind of, it's not tricky, but it just takes a little bit of insight. So remember I said the bifurcations occur when f of x is a fixed point, because we're studying the fixed points, and its derivative vanishes. Okay, in other words, the derivative of this whole thing vanishes. Okay, and those are the conditions you need to be able to find S1 and S2. So let's simply write down these two equations. Okay, and we basically might not be able to find them exactly in closed form, but we will be able to find them as a function of x. So remember now, f of x is a function of r, x, and k. Okay, we have two equations over here, and we can actually solve that for r and k in terms of x. So let's write them down. F prime equals to 0 is simply found by taking the derivative of this thing, and there we have it. So the derivative of this first term is simply r minus the derivative of r times x squared over k, which is this thing, minus the derivative of this beast, which is that thing. Okay, so that's the one equation. The equation for the fixed point, which is just simply f of x equals to 0, we can massage it a bit, and we can notice that this term over here, we can try and get an expression for it by simply noticing that if we were to put this term on the left-hand side and leave the others here and divide through by x, we get the following expression. Okay, so we're now going to put this into there, and what we're then going to get is that r of x is equals to 3x cubed over 1 plus x squared squared. So we've basically gotten r parameterized by x out of these two equations. We then take this thing and put it back into one of those two equations, and we can actually get 1 minus x over k equals to 1 plus x squared over 2x squared. In other words, we've basically put the expression of for r in over there, okay, and over there, and then we get that this is equals to that, and we can divide by r to actually get that. Okay, and then we can solve for k by simply multiplying through by a minus, subtracting 1 from that side and inverting it, and then we get k as a function of x is equals to 2x cubic x squared minus 1. Okay, So there's a little bit of algebra involved here, but all you have to do is notice that you have two equations from the fixed point condition, as well as the fact that you have a bifurcation occurring. Bifurcations always occur when the derivative vanishes at the fixed points. And then you solve these two equations to get your two parameters r and k in terms of x. And then when you've done that, you have these two parametric expressions for the parameters. And what we now want to do is make a plot of where these curves actually are. Okay, and we call that the bifurcation curve. So this is now the third plot, or the fourth plot we're introducing. It's a bifurcation curve is simply a plot in parameter space of where the nature of the solution changes. So for this particular example, we want to plot these parametric curves. And when we do it, a good thing is to examine the nature of the functions at the limits, when x gets very large, when x gets very small, and when the derivatives change. So when and an additional place that's interesting is wherever this thing goes infinite, wherever one of the denominators goes to 0. So that's what we're looking at first. If x goes to 1, right, then this thing goes to 0 and k goes to infinity. Okay, so as x goes to 1, k goes to infinity, so we effectively have an asymptote. If k goes to infinity, x equals to 1, r, actually, which is dependent just on x, goes to 1 plus 1, which is basically 2, squared. So that's 2 over 4, so that's a half times 1. Okay, so then r goes to a half. So we know that the solution asymptotes over here as x goes to 1, k goes to infinity, and the solution asymptotes over there to r equals to a half. So we immediately put that in. The next thing is where we work out the derivatives. We know that dk dx stops changing with x at the same point where dr dx starts changing with x, and that occurs when x is equals to the square root of 3. So to work those things out, you basically say put dr dx, you work out the derivative of r with respect to x, and set that to 0 and solve for x, and you'll find that occurs at x equals to the square root of 3, and it turns out that dk dx vanishes at the same point. Okay, so this is a point where the graph goes through, and you can immediately plot the point. If x equals to the square root of 3, you can immediately work out from here what r is as well as what k is. Okay, and then it simply goes from this point. As k increases, it goes to approaches r equals to a half from above. The second thing we can note is that as x goes to infinity, right, k goes to infinity with x because k also gets very large, but r goes to 0. Okay, so there's another asymptote over here at the line r equals to 0. Okay, x and k go into infinity, r goes to 0, and 0 is down there. And so you can actually draw the second graph in where you have r equals to 0. So these things are the curves, and the only two curves that satisfy this parametric equation, and this is called our bifurcation curves. Okay, so just another thing to note, if we go back to this graph over here, we have that, remember, if r is any value and k is small, then we have this picture over here that we only have one fixed point. Okay, so we only have one fixed point over here, and in fact we only have one fixed point until we go over the bifurcation curve, so we have one fixed point all the way over here. Now if we look at this graph, if k is large and R is large, then we also only have one fixed point, because then we have this blue line over here and we only have one fixed point over there. But if we decrease it and we get to the bifurcation curve, which is this purple over here, then we have two fixed points. If we decrease it further over here, which lies in the case between the two purple lines, we basically have three fixed points. So over here we have three fixed points corresponding to the blue. And then we cross the line again and we again have one fixed point. These two curves over here, S are S1, basically that point for any x, and S2, which is this point over here. Okay, so these lines are the lines in parameter space in which you only have two fixed points. Oops, sorry. Okay, so given this bifurcation curve, this is now how the nature of the solution changes. I just also want to show you what happens to the actual phase space diagram. Okay, so here's our bifurcation curve that we worked out in R and K. We're going to start and we call the situation where you only have one fixed point over here for small carrying capacity, the refuge fixed point. Sorry, for small r, the refuge fixed point. We're going to call the second one the outbreak fixed point. Okay, and you'll see why we did this now. And then we're going to call this case where we have three fixed points the bistable state. And so I want to show you what the phase space diagram looks like in each of these cases. So suppose you were to start, you look at your differential equation and you were to choose your parameters to be here in the bistable place where you had three fixed points. Okay, and you were then to draw the right-hand side of the graph and analyze it just as we did in the previous two lectures. You would get something like this. You would actually get your three fixed points in addition to the zero fixed points. You would put in your arrows where the graph is positive, you move to the right. Where the graph is negative, you move to the left, and you would be able to get the stability of fixed points. So here is your a stable fixed point. Over here is a large stable fixed point, and that separating the two is an unstable fixed point. So let's now see what happens. Oh, and just these fixed points have names. So this is the case where we have the refuge population of insects. In other words, the insects that are not really any problem at all. They're just there. Every garden has a few locusts. Every forest has a few budworms. Nobody cares. If the model was explaining Master KG, he's just become famous in South Africa. Some of the DJs play his music, but nobody abroad is really dancing to it. So the second fixed point represents the outbreak level. In other words, where there are so many locusts, we have a swarm, or so many budworms, we basically are eating the whole canopy of the forest, or Master KG has gone viral. Okay, so you have two possible solutions, points where the solution can go to, and there's something that separates them. Okay, and that thing that separates them is the threshold. And the threshold means if you have a population more than the threshold, you're going to have it's going to run to the outbreak solution. If you have a population less than the threshold, it's going to run to the refuge solution. And now suppose we change the parameters, because that's basically what the people that were going to manage the forests were going to do, is they were going to change some of the parameters to try and stop the outbreak. And they wanted to know what to change. So here, for example, if you change R, you keep K fixed and you increase R, instead of having the blue graph of the differential equation, you have this pink one. You still have a refuge population of insects, you still have an outbreak population of insects slightly better, and you still have the threshold, but the threshold has moved closer to the refuge population. So you have a smaller set of initial conditions that will lead to the refuge, and it becomes more likely for a random set of initial conditions that you'll run to the outbreak solution. If you eventually go to the bifurcation point, you have that the threshold is starting to disappear, right? And your refuge population is colliding with the threshold, and therefore this thing isn't even a stable solution anymore, it's a metastable. So any little knock on the solution here will make it run to the outbreak level. In this case, where you have changed your parameters so that you choose R enough that it lies above S1, the S1 curve, you basically have only one stable fixed point, and that's here at the outbreak level. Okay, so you no longer can have the refuge population, you always are going to go to the outbreak problem. If you do the reverse, if you go back to this blue solution and you decrease R, you can actually move the threshold higher, and so it's a more stable refuge population, less likely to have an outbreak. If you move it even higher, eventually the possibility of having an outbreak collides with the threshold, and that's also metastable. So what you're basically going to do is you're going to go to your refuge population, and here you have a very safe, stable forest where there is no chance of an outbreak whatsoever. So the forest management people actually wanted to drive it to the state, and they wanted to know how to change the knobs to make that possible. So that's going to conclude this lecture. I think we've got a feel for what the equations do. In the next lecture, we'll once again look at this problem, but just in a little bit more detail, and introduce some of the terminology that's going to be used. Thank you very much.